So now that we've talked water cycle, we need to start talking about where all of this is truly occurring and why this is occurring. So let's start describing Earth's atmosphere. We are now focusing in on Middle School Earth Science Standard 2-6, which states that you will be able to use models to describe how energy transfer impacts atmospheric and oceanic circulation to determine a regional climate. So we're not going to focus in on the oceanic circulation, but just the atmospheric. By the end of this lesson, you should be able to describe the makeup of each layer in our atmosphere, identify the temperature of layers and their correlation with one another, order the layers of the atmosphere from closest to the surface to furthest away, and then also describe the importance of each layer. Oddly enough, each layer plays a major role in our entire livelihood. So make sure that you have your notes in front of you and let's get going. So what is the atmosphere? The atmosphere is defined by your book and scientists is just a thin layer of gases surrounding the Earth. Now, obviously, we know that thin is relative to the size of the object. When we are thinking about the Earth as a whole, the atmosphere doesn't take up much of its actual radius, but rather as compared to the Earth, it's really thin, even though it extends a couple hundred kilometers up into what we know as space. So why is the atmosphere important? Well, as we have kind of learned back in quarter one with astronomy, our sun is constantly projecting and throwing out UV radiation. So ultraviolet radiation is coming from the Earth from the sun directly toward the Earth, leading it to need some sort of protection so that it doesn't literally microwave us to death. It provides the necessary gases to sustain life, so oxygen, carbon dioxide, nitrogen, helium, things like that. This is where a majority of our fresh water is actually being stored. Our atmosphere holds a lot of water. It regulates our temperatures so that we have the temperature that's suited for human life and other multicellular organism life to be able to thrive. And then finally, it gives us our weather and our circulation patterns and things like that. So it is helping us live. So as we've discussed in geologic time, our atmosphere has not always been the way that it is today. Our early atmosphere was actually really, really hot. There was a lot of what we now consider greenhouse gases within it, to where it had to cool significantly. During this cooling process, water vapor condensed, causing it to rain and well, continue to rain, which was important for cooling down our entire Earth as a whole. As we know, after getting dumped on day after day in the more recent weeks, the days where it's raining, it tends to be cooler as compared to the days that follow as the water is beginning to evaporate again. And then finally, as it rains and gets a lot of that greenhouse gases out of the air, we start seeing photosynthetic organisms absorbing the excess amounts of carbon dioxide out of the atmosphere and start producing the oxygen that was truly necessary for life to be able to move forward. So our atmosphere has had to change as our Earth has changed in order to support the life that it brought. Oddly enough, everyone's like, oh, there's so much oxygen in the air. Well, no, there's really not. 78% of our atmosphere actually contains nitrogen. Only 21% is oxygen, and then another 1% is a couple different things such as water vapor, argon, carbon dioxide, and ozone. So the air that we're breathing is not necessarily oxygen, but it's more so nitrogen. So our respiratory systems have had to learn how to filter out the necessary oxygen, which is a small percentage, and filter and not allow for the nitrogen to start entering our bodies, because too much nitrogen is not good. So kind of just a breakdown. It's weird to think that our atmosphere is more nitrogen than it is oxygen, because we're told to believe that it is oxygen. That's how we breathe. So that should be the end of whole group. If you are moving on to working independently, make sure that you are following our CHAMPS expectations. You do have an exit slip at the end of this, and in the next day or so, you will be having a foldable that goes along with it. So please pay attention to your layers of the atmosphere, because it is important to understand after today. So let's talk about our layers of our atmosphere. Our Earth is just like a giant jawbreaker, all the way from the inner core, outer core, mantle, asthenosphere, if you want to count that in, and the crust. We then continue into our layers as far as troposphere, stratosphere, mesosphere, thermosphere, and exosphere. And then finally we reach space. So let's talk about what's going on in each of these spheres. This is a diagram to kind of give you an idea how thick our atmosphere truly is. So our atmosphere is only about 60-ish, not even, miles, about 90 kilometers from not necessarily the bottom of the ocean, but rather where a majority of us live at sea level. So from sea level up is only about 90 kilometers. So like I said, when we describe Earth's atmosphere as being thin, it's thin in relative to our entire Earth, being that our crust itself in some areas is about 100 kilometers deep. So our crust is thicker in some spaces than our atmosphere. You can see certain things where we have Mount Everest as the tallest mountain on our surface. It doesn't even break through the troposphere. The stratosphere is where we start seeing our ozone, and then we see where our weather balloons are headed up. Most rockets that orbit our Earth fall within that 60-kilometer or the mesosphere range, and meteors start to break down during that point in time as well. If you take a look at the temperatures, you'll see that there is kind of a back and forth in temperature changes. So we will talk about all those as we continue through each layer of our atmosphere. So let's get going. Starting with our troposphere. So from our surface where we are currently standing till about 15 kilometers above us, this is all considered the troposphere. This is where life is actually able to occur because it maintains the temperatures necessary for us to be able to do what we need to do. Within the troposphere, this is also where we are seeing our weather occur. Weather does not happen above the troposphere. That's why if you're ever in a plane and you're going through a storm, you're not really going through the storm, you're going just above it, because most planes fly just above the troposphere. So within our troposphere, what happens is at ground level, or at sea level, we are at a very steady-ish temperature if you were to take the average, sort of a thing. But as you leave Earth's surface and head into higher altitudes, or you work your way away from sea level, you notice that the temperatures tend to drop. This is why in mountainous regions, it can be 70, 75 degrees in the foothills, but as soon as you start going up into the actual mountains themselves, you start seeing snow. Temperatures tend to be cooler as you head higher up into the actual peaks of the mountains. And that's because the higher we get within our troposphere, the cooler it gets. We also drop our air pressure. That's why people who climb Mount Everest to its summit typically need to bring some sort of oxygen supplement, because there's just not enough up there, because there's not as much pressure or gravity keeping oxygen, which is a heavier element, up that high. So this is where we start seeing that decrease in air pressure, but also a decrease in temperature. Now, why do I point this out? Well, because when we go to the stratosphere, within our stratosphere, so from about 15 kilometers to 50 kilometers above Earth's sea level, we start to see an increase in temperature and an increase in pressure. And that is because the stratosphere contains our ozone layer. And the only job of our ozone layer is to just keep that ultraviolet light from the sun from reaching us here on Earth. And that's because, as you learned in 7th grade, ultraviolet light and radiation can cause DNA damage or changes to both plants and animals. Mild range being just sunburns. And I don't want to say just sunburns. Enough sunburns or damage to your skin is not good as well, but that's considered mild, versus complete DNA changes that can cause a severe mutation, which could cause harm to that organism. So as we're traveling up into the stratosphere, because its job is to absorb all this ultraviolet light coming from the sun, it's actually much, much warmer than at the higher levels or higher altitudes of the troposphere. Ozone is made out of O3, so it's a very heavy element, but heavy enough to kind of float where it's at, and not sink completely to surface level. So the pressure increases ever so slightly at this point in time. But it's important to know that as we go up through the troposphere, it gets really, really cool. But then as we start going up through the stratosphere, and the closer we get through the ozone layer, the warmer it actually gets. Now, not necessarily saying like middle of the Sahara Desert sort of a thing, but not good. Once you reach that 50 kilometers or so, all the way until about 85 kilometers, now all of these distances are very relative, depending on who's doing the measurements at what times of the year and during what times of the day. So, yeah, it can vary a little bit, but from about 50 to 85 kilometers is what we're considering the mesosphere. Now, the mesosphere kind of does what our troposphere does. With the increase in altitude, you actually get a decrease in temperature. This is just because, again, you're moving so far away from Earth's surface that the actual gravitational pull towards the Earth is not as strong. Within the mesosphere, we actually start getting a little bit of an overlap with the ionosphere. Now, we call it the ionosphere because this is where ions can start to do little things that we call solar storms. That's where any of those random particles being shot out from other planets, from the sun mainly, these ions get trapped within our ionosphere, and it makes little chemical reactions. As these ions reach the atmospheric ions that we already contain, it starts to emit a color because they're interacting with one another. These colors we then call our aurora borealis. So the reason why we can see the northern lights is because our ionosphere that overlaps with our mesosphere is breaking up all those particles to ensure that they don't make it to Earth's surface and do damage to us. So, important to know within the mesosphere, as you increase throughout the mesosphere, the cooler it gets. Now, thermosphere. So as you can kind of guess, thermo's short or means heat, temperature. So we have a change in temperature once again. So the thermosphere is from about 85 kilometers until about 500 kilometers. So this is where scientists really start getting iffy on how thick truly is the Earth's atmosphere. But as you increase in altitude throughout the thermosphere, you are also increasing your temperature. And that's because the job of the thermosphere is actually to start the process of catching space debris, such as meteors, and start breaking them down so that they don't reach Earth's surface and again do harm to us living things here on Earth. So because it has all that extra energy of these interactions of our atmosphere and random space junk and constantly, as much as we like to think that space is empty, there's a lot of energy out there trying to come into our atmosphere. So our thermosphere's job and part of the mesosphere is to break up those space nonsense so that it doesn't do harm to us on Earth. So again, as you increase through the thermosphere, you are also increasing in temperature. Finally, the exosphere. Exo, like we think of exoskeleton or outside. So this is the furthest it goes. This is where our atmosphere ends and space truly begins. We are only 100% aware of the exosphere because this is the last little bit of gravity to hold things within our orbit, such as satellites. This is the layer in which our satellites are orbiting and keeping it within geosynchronous to where we have things like standard time, GPS, things like that. So the exosphere is just that last little pull that the Earth can give to get to keep things within its orbit before it is lost to space. The exosphere is where our space station is currently orbiting and things like that. The exosphere can be anywhere from 500 to only 90 kilometers from Earth's surface out, sort of a thing, because again, it's that last little bit of gravitational pull. So here is what is happening typically as we are increasing in our altitude. Air pressure is highest at Earth's surface. So where we are at, where we're about sea level, granted nowhere near sea, this is the most amount of air pressure we will ever experience. But as you move away from the surface, because you don't have as much of that pull from Earth's gravitational pull, but rather than you're starting to interfere with the sun's gravitational pull, essentially. As you continue up into the atmosphere, the less pressure you're truly going to feel. And that's because there's just more space for things to be able to move around. So this first picture is a great explanation, just like down here at surface level where we are at, everything is held super strong to Earth's surface. That's why when we jump up, we come back down and don't go flying off into space. But as you increase in altitude, there is more and more space for these particles to be able to move around. So that's what's going on there. The second is just a graph to be able to kind of show you with the increase in altitude, the decrease in actual pressure that is felt, and it's at an exponential rate as soon as you leave that 10 kilometers above Earth's surface, which is above Mount Everest. And like it's showing the Boeing 747, that's where it flies. After that, it's just little to no pressure, clearly, until you get out to space. Now, temperature and altitude don't always go hand in hand, and that's because there are different gases and elements and things like that that are interacting. So as we increase in altitude within our troposphere and our mesosphere, we start to see that temperature drop because there's nothing really being held at that level, versus as you increase through the stratosphere and the thermosphere, you have other elements that are being held within those in those layers that help contribute to the amount of heat that can actually be like retained. So within the stratosphere, you have the ozone layer, which is absorbing a lot of UV radiation. And if you've ever stood in the sun just for like a minute, that warm feeling of just the sun looking upon you, if you can imagine that now holding all of that energy in one spot, that's what's going on in the ozone. And then within the thermosphere, it's receiving a lot of direct energy from the sun to begin with, because it's one of the last line, like it's the first line of defense from the sun's UV radiation to us. So it does a lot of the heavy lifting. So that this is also where a lot of space junk is starting to be burned up. And if you just like felt above a pot of boiling water, like it's kind of like that, where it's starting to get all that excess heat and stuff. So that's what's going on. Now you'll also notice that at certain places it seems to be kind of stagnant or stand straight up, and that is because it is at the pauses. Literally as they sound. So we have the tropopause, the stratopause, the mesopause, the thermopause, things like that. Because this is where there's kind of just a pause. It's this weird like gray area between the different layers. So we tend to just average it out and it seems to be somewhat stagnant. And then as soon as you start decreasing and or increasing in altitude into the next layer or vice versa, you can start seeing those changes happen. So just so you're aware, not going to test you on the different pauses, but just there's always gray area. It's like, where does one thing end and the next begin? So awesome. You should have completed your notes, and if that is the case, then make sure you get those turned in. There is an exit flip, and we will be moving on into our foldable in the next day or so. Thanks. If you have any questions, please feel free to ask. Thanks, guys.